Apportionment. Apportionment is the problem of dividing up a fixed number of things among groups of different sizes. In politics, this takes the form of allocating a limited number of representatives amongst voters. This problem, presumably, is older than the United States, but the best known ways to solve it have their origins in the problem of assigning each state an appropriate number of representatives in the new Congress when the country was formed. States also face this apportionment problem in defining how to draw districts for state representatives. The apportionment problem comes up in a variety of non-political areas too, though. We face several restrictions in this process. Apportionment rules. 1. The things being divided up can exist only in whole numbers. 2. We must use all of the things divided up and we cannot use any more. 3. Each group must get at least one of the things being divided up. 4. The number of things assigned to each group should be at least approximately proportional to the population of the group. Exact proportionality isn't possible because of the whole number requirement, but we should try to be close, and in any case, if Group A is larger than Group B, then Group B shouldn't get more of the things than Group A does. In terms of the apportionment of the United States House of Representatives, these rules imply: 1. We can only have whole representatives. A state can't have 3.4 representatives. 2. We can only use the currently 435 representatives available. If one state gets another representative and another state has to lose one. 3. Every state gets at least one representative. 4. The number of representatives each state gets should be approximately proportional to the state population. This way, the number of constituents each representative has should be approximately equal. We will look at 4 ways of solving the apportionment problem. 3 of them, Lowndes' method is the exception, have been used at various times to apportion the U.S. Congress. Although the method currently in use, the Huntington-Hill method, is significantly more complicated. Hamilton's method. Alexander Hamilton proposed the method that now bears his name. His method was approved by Congress in 1791, but was vetoed by President Washington. It was later adopted in 1852 and used through 1911. He begins by determining to several decimal places how many things each group should get. Since he was interested in the question of congressional representation, we'll use the language of states and representatives, so he determines how many representatives each state should get. He follows these steps. Hamilton's method. 1. Determine how many people each representative should represent. Do this by dividing the total population of all the states by the total number of representatives. This answer is called the divisor. 2. Divide each state's population by the divisor to determine how many representatives it should have. Record this answer to several decimal places. This answer is called the quota. Since we can only allocate whole representatives, Hamilton resolves the whole number problem as follows. 3. Cut off all the decimal parts of the quotas, but don't forget what the decimals were. These are called the lower quotas. Add up the remaining whole numbers. This answer will always be less than or equal to the total number of representatives, and the or equal to part happens only in very specific circumstances that are incredibly unlikely to turn up. 4. Assuming that the total from step 3 was less than the total number of representatives, assign the remaining representatives, one each, to the states whose decimal parts of the quota were largest until the desired total is reached. Make sure that each state ends up with at least one representative. Note on rounding. Today we have technological advantages that Hamilton and others couldn't even have imagined. Take advantage of them and keep several decimal places. Example 1. The state of Delaware has 3 counties: Kent, Newcastle, and Sussex. The Delaware State House of Representatives has 41 members. If Delaware wants to divide this representation along county lines, which is not required, but let's pretend they do, let's use Hamilton's method to apportion them. The populations of the counties are as follows from the 2010 census. 1. First, we determine the divisor. 897,934 divided by 41 equals 21,900.82927. 2. Now we determine each county's quota by dividing the county's population by the divisor. 3. Removing the decimal parts of the quotas gives. 4. We need 41 representatives, and this only gives 40. The remaining one goes to the county with the largest decimal part, which is Newcastle. Example 2. Use Hamilton's method to apportion the 75 seats of Rhode Island's House of Representatives among its 5 counties. 1. The divisor is 1,052,567 divided by 75 equals 14,034.22667. 2. Determine each county's quota by dividing its population by the divisor. 3. Remove the decimal part of each quota. 4. We need 75 representatives and we only have 72. So we assign the remaining 3, one each, to 3 counties with the largest decimal parts, which are Newport, Kent, and Providence. Note that even though Bristol County's decimal part is greater than 0.5, it isn't big enough to get an additional representative because 3 other counties have greater decimal parts. Hamilton's method obeys something called the quota rule. The quota rule isn't a law of any sort, but just an idea that some people, including Hamilton, think is a good one. Quota rule. The quota rule says that the final number of representatives a state gets should be within one of the state's quota. Since we're dealing with whole numbers for our final answers, that means that each state should either go up to the next whole number above its quota or down to the next whole number below its quota. Controversy. After seeing Hamilton's method, many people find that it makes sense. It's not that difficult to use, or at least the difficulty comes from the numbers that are involved and the amount of computation that's needed, not from the method. And they wonder why anyone would want another method. The problem is that Hamilton's method is subject to several paradoxes. 3 of them happen on separate occasions when Hamilton's method was used to apportion the United States House of Representatives. The Alabama paradox is named for an incident that happened during the apportionment that took place after the 1880 census. A similar incident happened 10 years earlier involving the state of Rhode Island, but the paradox is named after Alabama. The post-1880 apportionment had been completed using Hamilton's method and the new population numbers from the census. Then it was decided that because of the country's growing population, the House of Representatives should be made larger. That meant that the apportionment would need to be done again, still using Hamilton's method and the same 1880 census numbers, but with more representatives. The assumption was that some states would gain another representative and others would stay with the same number they already had, since there weren't enough new representatives being added to give one more to every state. The paradox is that Alabama ended up losing a representative in the process, even though no populations were changed and the total number of representatives increased. The new states paradox happened when Oklahoma became a state in 1907. Oklahoma had enough population to qualify for 5 representatives in Congress. Those 5 representatives would need to come from somewhere, though, so 5 states presumably would lose 1 representative each. That happened, but another thing also happened. Maine gained a representative from New York. The population paradox happened between the apportionments after the census of 1900 and of 1910. In those 10 years, Virginia's population grew at an average annual rate of 1.07%, while Maine's grew at an average annual rate of 0.67%. Virginia started with more people, grew at a faster rate, grew by more people, and ended up with more people than Maine. By itself, that doesn't mean that Virginia should gain representatives or Maine shouldn't, because there are lots of other states involved. But Virginia ended up losing a representative to Maine. Jefferson's method. Thomas Jefferson proposed a different method for apportionment. After Washington vetoed Hamilton's method, Jefferson's method was adopted and used in Congress from 1791 through 1842. Jefferson, of course, had political reasons for wanting his method to be used rather than Hamilton's. Primarily, his method favors larger states, and his own home state of Virginia was the largest in the country at the time. He would also argue that it's the ratio of people to representatives that is the critical thing, and apportionment methods should be based on that. But the paradoxes we saw also provide mathematical reasons for concluding that Hamilton's method isn't so good, and while Jefferson's method might or might not be the best one to replace it, at least we should look for other possibilities. The first steps of Jefferson's method are the same as Hamilton's method. He finds the same divisor and the same quota and cuts off the decimal parts in the same way, giving a total number of representatives that is less than the required total. The difference is in how Jefferson resolves that difference. He says that since we ended up with an answer that is too small, our divisor must have been too big. He changed the divisor by making it smaller, finding new quotas with the new divisor, cutting off the decimal parts, and looking at the new total until we find a divisor that produces the required total. Jefferson's method. 1. Determine how many people each representative should represent. Do this by dividing the total population of all the states by the total number of representatives. This answer is called the standard divisor. 2. Divide each state's population by the divisor to determine how many representatives it should have. Record this answer to several decimal places. This answer is called the quota. 3. Cut off all decimal parts of all the quotas, but don't forget what the decimals were. These are the lower quotas. Add up the remaining whole numbers. This answer will always be less than or equal to the total number of representatives. 4. If the total from step 3 was less than the total number of representatives, reduce the divisor and recalculate the quota and allocation. Continue doing this until the total in step 3 is equal to the total number of representatives. The divisor we end up using is called the modified divisor or adjusted divisor. Example 3. We'll return to Delaware and apply Jefferson's method. We begin as we did with Hamilton's method, by finding the quotas with the original divisor, 21,900.82927. We need 41 representatives, and this divisor gives only 40. We must reduce the divisor until we get 41 representatives. Let's try 21,500 as the divisor. This gives us the required 41 representatives, so we're done. If we'd had fewer than 41, we'd need to reduce the divisor more. If we had more than 41, we'd need to choose a divisor less than the original but greater than the second choice. Notice that when the new lower divisor, the quota for Newcastle County, the largest county in the state, increased by much more than those of Kent County or Sussex County. Example 4. We'll apply Jefferson's method for Rhode Island. The original divisor of 14,034.22667 gave these results. We need 75 representatives and we only have 72, so we need to use a smaller divisor. Let's try 13,500. We've gone too far. We need a divisor that's greater than 13,500 but less than 14,034.22667. Let's try 13,700. This works. Notice, in comparison to Hamilton's method, that although the results were the same, they came about in a different way and the outcome was almost different. Providence County, the largest, almost went up to 46 representatives before Kent, which is much smaller, got to 12. Although that didn't happen here, it can. Divisor adjusting methods like Jefferson's are not guaranteed to follow the quota rule. Webster's method. Daniel Webster, 1782 through 1852, proposed a method similar to Jefferson's in 1832. It was adopted by Congress in 1842 but replaced by Hamilton's method in 1852. It was then adopted again in 1901. The difference is that Webster rounds the quota to the nearest whole number rather than dropping the decimal parts. If that doesn't produce the desired results at the beginning, he says, like Jefferson, to adjust the divisor until it does. In Jefferson's case, at least the first adjustment will always be to make the divisor smaller. This is not always the case with Webster's method. Webster's method. 1. Determine how many people each representative should represent. Do this by dividing the total population of all the states by the total number of representatives. This is called the standard divisor. 2. Divide each state's population by the divisor to determine how many representatives it should have. Record this answer to several decimal places. This answer is called the quota. 3. Round all the quotas to the nearest whole number, but don't forget what the decimals were. Add up the remaining whole numbers. 4. If the total from step 3 was less than the total number of representatives, reduce the divisor and recalculate the quota and allocation. If the total from step 3 was larger than the total number of representatives, increase the divisor and recalculate the quota and allocation. Continue doing this until the total in step 3 is equal to the total number of representatives. The divisor we end up using is called the modified divisor or adjusted divisor. Example 5. Again, Delaware with an initial divisor of 21,900.82927. This gives the required total, so we're done. Example 6. Again, Rhode Island with an initial divisor of 14,034.22667. This is too many, so we need to increase the divisor. Let's try 14,100. This works, so we're done. Like Jefferson's method, Webster's method carries a bias in favor of states with large populations, but rounding the quotas to the nearest whole number greatly reduces this bias. Notice that Providence County, the largest, is the one that gets a representative trend because of the increased quota. Also, like Jefferson's method, Webster's method does not always follow the quota rule, but it follows the quota rule much more often than Jefferson's method does. In fact, if Webster's method had been applied to every apportionment on Congress in all of American history, it would have followed the quota rule every single time. In 1980, two mathematicians, Peyton Young and Mike Belinsky, proved that we now call the Belinsky-Young impossibility theorem. Belinsky-Young impossibility theorem. The Belinsky-Young impossibility theorem shows that any apportionment method which always follows the quota rule will be subject to the possibility of paradoxes like the Alabama, new states, or population paradoxes. In other words, we can choose a method that avoids those paradoxes, but only if we are willing to give up the guarantee of following the quota rule. Huntington Hill method. The Lowndes method. Apportionment of legislative districts.